So I'm Sven. I'm a biostatistician, epidemiologist. I have a dual appointment, one at Karolinska Institute in Stockholm, where I come from just now, and one at Mount Sinai in New York. And the outline of my talk is, after a short introduction, to start the discussion on separating genetic risk from environmental risk. And I will do that using most examples from the Nordic countries. I will show how we know that how much is inherited genetic and how we know how much is inherited or environmental. And then I will go through a few case studies, a few studies we have published, and also introduce the Nordic registers in this. So that's the background. And I'll start just briefly where I came into this. So my background is in pharma. I started quite late in academia, working with cancer epidemiology at Karolinska, early 2000. And then I started working on autism through Avi Reichenberg, who many of you here may know. And then the situation looks like this. So we saw an immense explosion of autism cases around the world. This is from US CDC, showing 0.5% in prevalence in 1995, up to 1% in 2009. I Googled and I found this one also from Israel, which you probably know more than I do. And here is 0.5% reported in 2007, up to 1.3 in 2018, I think. And from my part of the world, we did this study in 2015, I think, combining data from Denmark, Sweden, Finland. And we see the same thing, it's kind of just exploding. What's noteworthy here is the difference in prevalences. So we see on the y-axis, we see the prevalence of autism. And then there are different development for different birth cohorts. And we can see that the increase hits all cohorts at the same time. So it's nothing strange going on. It's kind of, and we see Western Australia, the same. They are a lot low prevalence due to different ascertainment and a different database, but the pattern looks the same. It's the same kind of increase. And even though there is increase everywhere, there are also quite large regional variations. So there are a few flashes here. I think it's CDC from different states. So we see it's as low as 6 per 1,000 kids in Alabama, 9 in Wisconsin, and up to 22 cases per 1,000 in New Jersey. And how can this be? This is a map of Sweden. There are different counties. And I'll color them here after the prevalence rate. This is quite old data, but it illustrates the points. It's around 2009. And we see the lighter areas, it's below 0.3%, and the red and orange is 1.3 to 1.5. So again, how come we see these differences? And then there was a lot of discussion how this come. Is it only increasing awareness, or is there also a change in environment? The uptake in IVFing, the older parents, could it be chemicals, et cetera. Or is it a shift in etiology? And this is kind of one motivation why we want to see and estimate how much come from the genetic inherited side and how much is from environment, and in that case, which cases. So that's one way to enter this. And before I show the results, I want to just briefly introduce the Nordic registers, because I think that will help the understanding and maybe serve as a background noise for your discussions later. So in Sweden, the registers have a very long history, and it's worth mentioning because I think this register sits in a society, and they belong there. It's so the Swedish population register started in mid-17th century, and it was a wish from the government or the king to count the population size, so he know what he could use in wars and what the wealth was. So they did that counting. It was when done by the church, so they registered all the births, all the deaths, and also events like marriage and other things, church-like. And they actually kept doing that until 1991. Then the tax office took over, which improved the things a lot. So, of course, yes. And I thought it was a bit funny story that the population count showed that it was about 2 million Swedish people. Finland was then part of Sweden, so Finland was 400,000. And they kept it secret because it was too low. So what would the horrible Danes say, and then the Russians? Would they come at us? But then I felt that this is not so funny, actually. It's still like this, isn't it? In the US, when they have the polls about the voting, in China, and everywhere. So, but it has a long history and is kind of well accepted in society. We haven't had any too bad experiences in working with them. So we have the registers from the whole lifespan. We start early life, medical birth register. This is maybe maybe the most important register for research. So all births in Sweden are recorded together with, linked with child and mother, and important information around the births, like birth weight, gestational age, also diagnosis in the kid, in the mother, etc., etc. So it's more or less a research register. And then you see other registers throughout life. We have a cancer register where all malignant cancers are reported by law since 1958. We have different registers for education, income, prescription, or no, not prescription, which can give information of social effects. Prescription register is in place too for medications. The medications handed out in the public. And then up to late life where we have cause of death. And all this then sits in a system with publicly financed health system and publicly utilized health system. So essentially all health care in Sweden goes through this system. Later years there have been changes, more privatization, so that changed a little bit, but it's still very much the case. And the development later year is the development of a lot of kind of so-called quality registers. So the government hand out money for kind of special interests like psychiatry or MS or rheumatoid arthritis, etc. So this will be for the future. There are also registers which are genetically informative. We have a twin register, which is based at Karolinska Institute. Population register, migration, immigration, and then an important register, which is multi-generation register. So the background for this register is the introduction of the personal identification number in 1947. So all 15-year-olds in Sweden were kind of included together with the parents, and then all kids born in Sweden since then are included in this register. And there have been changes across time here as well. So the system was computerized in 1961, and then you had to be alive in Sweden to be in the register. Later, there were attempts to put them back in again when they realized how important this is. And currently, more than 10 million index persons together with their parents and things. And this allows us to build up this kind of pedigree. And we had one publication where we look at autism risk across generation. So in this case, how is the risk associated with maternal and paternal age? How is that spread to the next generation, to the grandchildren? So that I will not go deeper into that, but I just mentioned that as an example. Autism, there is also then the patient register, and this is where primarily we have our autism ascertainment for research. And the patient register was put in place in 1964, was quite useless until 1973, because it was one county at a time included. So the early years, poor quality and just being introduced. From 1973, we have nationwide all inpatient psychiatric care, which was pretty perfect then because most psychiatric care was in hospitalized, more, at least when we talk about diseases. And we have, the patient register uses ICD system. And from 1987, we have ICD-9, and that's where we have autism introduced in the register. So before that, we don't know anything about autism, unless we want to speculate about schizophrenia in childhood and things. But from there on, we can follow. From 97, there is a shift to ICD-10, and in a few years, I guess we will have ICD-11, and then. So we have changes in the ascertainment of autism across time as well. Around 99-ish, up to 2005, county by county, outpatient specialist care is included as well. And what's included here is, as I write on the top, it's an administrative system actually. So, and it includes all specialist care, so not the general practitioners. And for each clinician who want to get paid for doing the treatment, he has to put down a diagnosis. And it's probably good incitament to have it up and running. For autism specifically, I can say that there is no screening or anything. There is a 4-year health checkup for cognition and kind of general health. And there in the public finance system, the kid will be picked up if the nurse or maid or the team around it picks up anything in the behavior. And then the school system is pretty much the same. The kids are looked after and they're kind of moved into the system and healthcare. And then, so this is kind of what was generating our data. And then it also it highlights all the problems we have in analyzing. Is the sound? Oh, right. Okay, thank you. Sorry. And here is a map of the Nordic countries, just so you know. It's the green part in the middle, that's Sweden, about 10 million. To the yellow in Norway, the blue is Finland, and the red is Denmark. So each of them about half the size of Sweden, between the finger and thumb. Iceland is part 2, but that is only 300,000 people. So usually not included when we work with the whole Nordic countries. You can see the birth rate are very similar, the life expectancy, death rates, the demography is very similar of an aging population. And all countries have a welfare state model with publicly financed health system. Language-wise, we can understand each other besides Finland, but 5% of Finland talk Swedish, and it's kind of Sweden and Finland have been the same country for the longest time period, and Denmark and Norway. So there are cultural bonds, there are language, and then there are a lot of things that kind of binds these countries together. And then we also then have these registers in the different countries. So this was put up for a Nordic collaboration I was part in, and it just illustrates for the different countries that we have very similar registers. So you find the medical birth register, and the difference is when they were initiated in the different countries. And here Norway was really early in 1967, and Denmark 73, Sweden 73, and then the late one was Finland 87. The patient register I mentioned, the same there, it varies. The cancer register, Denmark was the first one in 1943 during the war. I'm not sure why they decided then to have a cancer register. in Sweden from 58. We see some differences where Norway and Sweden were later on in including the kind of social aspects of the register, so the occupation and income, etc. So again, there are differences, but there are also a lot of similarities. And there are, given all this together, there are, of course, implication on the research and statistical and analytical changes. So everything is longitudinal, as we see. You're born into the system, that is one date. Then you follow up, you have your diagnosis, all patient contacts or clinical contacts are recorded. So that is something we can and we have to address in the analysis, which kind of complicates things. And they're open for a lot of biases, so the different changes across time, for instance. And we also have then the great possibilities to take care of all these biases. So first of all, that we can enumerate the whole population, so we essentially avoid all selection biases. So everyone are there. And then, due to the richness of the registers, we can do a lot of research. So exemplified in this small diagram here with outcome being autism, and then one exposure E, which could be type 1 diabetes, for instance. And what's important in all epidemiological research is, of course, to avoid confounding, which would be the C and the arrows here. So the C could be birth year. And since birth year is driving autism, we've seen the rates go up all the time. And the C birth year could also drive the diagnosis of type 1 diabetes because of increasing obesity, etc., in the population. So the birth year underlying could create a false association between autism and type 1 diabetes. And by putting birth year into the equation, we can break this dependence and we come closer to the underlying truth. And then we can put in yet other confounders here, of course, like maternal age, paternal age, and whatever we like to think about. So later, maybe 5 years, that has been a big and fast development towards causality and trying to understand mechanisms more. And that is exemplified here. So in this study now on type 1 diabetes, where we adjust for confounding, we can also study mediating effects. And one such could be preterm birth. So about 30% of type 1 diabetes mothers, their offspring are born preterm. And we know that preterm is a major risk factor for autism. So this comes in as a mediator. And that allows us to disentangle these things and try to understand what is actually diabetes and what comes secondary from the preterm. And then we can kind of decide what is important or not. So this is what we can do. And also important, maybe as important, is replicability across the countries. Since they are very similar, we can do one study in Sweden, we can replicate the result in Denmark, and see for differences. And for rare exposures, also, of course, pooling and get higher precision. And then there, of course, not everything is perfect. So what we are lacking to a large degree, and which you may solve maybe in the kind of database you're trying to build up here, is biological markers that we are essentially lacking. Details about the phenotype. So we will have information if the kid has autism, yes or no, and the date, but we don't really know what is it, or what's the feature of the phenotype. So that is to a large extent missing. And then the question, can we get access to these data? And of course, yes. There is, and I bring this up because sometimes, especially when I meet people in the US, some seem to think that the data sits in Excel spreadsheet and they can just be spread around. But these are, of course, very sensitive data. Ethics boards are required, which is a fairly long process, as any ethics approval. That makes also necessary to have a contact in a Swedish university. Once you have that ethics approval, you can go to the register holder, to the government, and ask for permission to use the data. And the government wants us to use the data because it's seen as a national research resource. But still, we have to do that. And then the lawyers at the registers take over, and their only view is that of privacy. They are like this. And they don't care about research, they care about privacy. It can be very annoying. And so the result is that talking to them, we need to set up a clear hypothesis. We show them the analysis that we will use the variables in this way. So you see, we do need them. And we need this diagnosis. And then they can say, but you haven't motivated this diagnosis. I will not give it to you. So we have to come back then. And so it's a process. And in the end, we'll have the data. But it takes time. Then the data are controlled under the EU law, GDPR, which controls how we can deal with the data. And yeah, that's it. Then we can start working. And sharing the data, in principle, should be easy under the GDPR, so I can sign an agreement with the university in Norway, send the data there, and we can do the analysis. But there are also legal or local interpretations. So typically in Denmark, they don't want to share the data. They are happy to share, but they must sit then in Statistics Denmark in Copenhagen. So you have to go there and do the analysis. So yeah, there are kind of issues here and there. Okay, so that's a background, and then the question to if autism is a genetic disorder. I thought I could start with this. It's a small, neat example from the UK. It's called Rutter and Folstein from 1977. What they did was to create a small data set of 21 twins, and they selected the twins, so one of the twins, at least in the twin pair, had autism. And then they divided the twins into two groups. So they divided them in the M set, the one-egg twins, and the D set, the two-egg twins, and looked at them. And the underlying idea was, of course, that the M set twins share 100% of the genes, and the D set only 50%. So if there aren't any differences, they argue that it must be due to the inherited or genetic effects. And this is what this very tiny manuscript shows, is half an A4 page, I think. So among the 21 pairs, 11 are M-set, and among those 11, it's about 40% who are concordant, so both twins have autism. And for the D-set, it's 0, so none of them agree. And then they argue this is a strong support that autism is a genetic disorder. So this is clever, and I think these ideas underlays everything that we have done later and what I will show you. So it's dividing the data or the population we're working with in different parts with different information on genetic relatedness or environmental relatedness or closeness. And that takes us to the concept of heritability. And this concept is first of all, it's a population measure. It acts on variation in autism risk in the population. So the different factor that makes one be diagnosed with autism and another one not, and why this varies. It's these variations we are working with, and we are trying to divide these variations in different groups. So we try to divide them up and say that this part of the variation comes from genetics, and this part comes from the shared environment, and this comes from the environment. And there could be yet other groups. And what it measures, and then we want to know how important are the genetic factors compared with the total variation. And it's a useful, not useless, measure in that sense. But it should not be interpreted on an individual level, because it doesn't tell me anything about my risk or my kids. And it doesn't quantify the number of genes. And it doesn't mean either that it's the same genes in a family or in a group. And it's nothing predictive in it. So it's totally a population measure. And used as that, it's quite useful. So an ABC of calculating heritability then, again, let's go back to the twins. So we have the MZ twins, who share 100% of the genes in average, we should say, but I say 100%. The DZ twins share 50%, so half of it. And then we put in an assumption, and there are a lot of assumptions, as always in these models. And that is why we need to continue doing more and more research to check these assumptions and know that we are right. So the variance for the MZ can be divided in 100% from the genetics and 100% also from the environmental part. And the DZ, you can see the genetic part is reduced by half, so it's 50% from the genetic component and still 100% of the environment, because we assume that all twin pairs share the same environment. And then we can simply take the difference between these variances. So the environmental part takes out, and what we have left is 0.5 times the genetic part, so we have to double that one. And an example here then, using correlations. So if the MZ correlation is 0.5 and the DZ correlation is 0.2, we can simply take the difference, which is 0.3, and we take that times y, and then it's an estimate of 0.6. So this is kind of a simplified using the twins. And there have been a lot of studies done in the twins, especially the early ones. But there were some concern. One is that some people argue that twins are special. They are not representative of the whole population. And you can believe in that or not, but that is one kind of criticism. And then there is assumption like they are assumed to be independently ascertained. So when the parent comes into the clinician, they don't bring both twins, and they don't kind of work with them as a pair. But it's assumed that they take one twin, this is one person, then take the next twin as one person. So that's another assumption. And then another more obvious problem, I think, with twins is that they are not so common. They are few. And this results in wider confidence interval, low precision, and we want to have better precision. So what to do? Then we started working on the Swedish population and the pedigree I showed you earlier. So this was, we published this in 2014 and 17, where we used the whole Swedish population. And so we created pedigrees like this. And we included the twins, but we also included, more important, the full siblings, the half siblings, which we could split in paternal half siblings and maternal half siblings. And then it says full cousins, but they were actually not part of these calculations. But still, the cousins could go in there as well. And we can see that the same reasoning as for twins can be done on the population. So the full siblings share 50% of the genes, the maternal half siblings 25, paternal 25, cousin 12.5, etc. We could go further down in the pedigree. And then we put in these assumptions again, and we assume that the full siblings share 100% of the shared environment. And shared environment would be anything that makes them similar. And that would be typically something from when they are born. They eat the same diet, they live in the same house, breathe the same air, all these kind of exposures are shared. For the half siblings, we make the same assumption, 100%. For the paternal, we make an assumption which can be discussed. So we say that it's 50%. Today in Sweden, the sharing is equal in mothers and parents. So I'm a bit skeptical to this. But that's an assumption that need to go in. We use that one. If the assumption is wrong, there will be bias. And everything's fine, I think, just if we put it up and we are aware of it and we can address it maybe in the next study. So the same here, we assume independent ascertainment. We don't ascertain a family, we ascertain individuals. And that's it. And then we can look, this is another picture of how it works. So in this pedigree, so over to the left, we have the paternal half-siblings, and then we have the monozygotic twins. And on this red line here, we have bars showing the amount of contribution from the genetic side. And this is shared environment side, and we can skip the others. And so then we see that the paternal half-siblings, their contribution have 25% of genetics. The monozygotic twins share 100%, etc. So we use these different family types to contrast them like we did with the twins. It's just a little bit more complicated. The estimation is very complicated in a random minor model, but that can be solved. And I'll skip that one. And then I show you the results and the kind of the sequence we did. So we started in 2014 and 17. What we had then, this was the first family-based study. We included twins, full siblings, half maternal, half paternal. And we had follow-up until 2009. And we showed the heritability is 80%. So 80% of the contribution come from the genetic side. And the confidence intervals here are fairly narrow, actually. So we say it's between 79 and 87. I can't remember how many individuals we had in this, but probably children born from 87 to 2009 or 7 or something like that. It's 100,000 people born each year in Sweden, so approximately 2 million individuals. So that was one study. And then we went on, so in 2018, in another database, we removed the twins, or rather we didn't have the twins. But instead we put in the cousins. And together with again, the full siblings and maternal and paternal half-siblings. We extended the follow-up now to 2014, and we estimated again heritability to 85%, and then confidence intervals 73 to 87, so we kind of verified that. Then in yet another study, the year after, we used the same data. It's in 2018, but we added 4 other countries. So we included Denmark and Finland, and a small sample from Israel and Western Australia. And then we can look at the differences and similarities. So the 2 major countries here is Sweden, 10 million, and Denmark, 5 million, and follow up for a long time. And they are fairly similar. So the Danish is 80, so between 71 and 87. And we see that the confidence intervals for Denmark are wider, but overlapping with the Swedish, so kind of verifying. Israel looks the same, but yet wider. Finland, in this case, looks actually smaller. But confidence intervals, again, overlapping. So, and then we have the sample from Australia, which was really tiny, and a different ascertainment that showed also lower, but still overlapping. So in the same kind of area. The shared environment I didn't mention. So in the first studies, there were no hint of shared environment, and that has been a long debate. And it was a publication. Yeah, I will not go into that. And then we verified that in 2018, 2019, again with 2 buts maybe. So one is Finland, where it actually indicates that maybe there is a shared environment part there. And also for Australia, but that is so small and different ascertainments, I will not go into that. But Finland is worth mentioning because it's interesting that we see a difference. And why could it be? So if we look at what the statistical model picks out of the data, it must be something in the data. And if that reflects the truth or not is another question. but it's something that makes the Finnish siblings and cousins more similar. So maybe there is something in the Finnish system that kind of ascertains them differently. It could also be that I think in Denmark and Sweden, we followed individuals all the way up to age 30. Because actually when we look in the register, it's not like kids are born and there are no autism, and then age 4, everything comes and it flattens out. It's just a linear, and it goes on and on and on. So you have 18-year-old with autism, 20-year-old, etc., etc. And so that could also be influential. So there are different ways of looking to this, and kind of we'll see in the future the coming studies we will make and see what happens. 5 minutes. Oh, sorry. So my watch I've stopped, that's why. So I thought the time was kind of really slow. So I'm only half through. This is ridiculous. So I'll show you just a few things here. And what we can do in these studies is also look at individual risk, because I said heritability is a population measure. And that is quite useless. But I've had received quite a lot of emails from clinicians and families who wonder what's the risk. And we can look at this in these families as well. So we can, when we enumerate them, if we have a child with autism in the family, we can calculate what is the risk for the other parts in the family. And we did that and published, and we see the results here. You see them on this forest plot. You see the MZ twins, they are really off, but more common for the siblings. So we have full siblings. If you observe autism in one, the risk increase with a factor about 10 or 8 for the other one. And then it go down to 3 or 4 for half siblings and 2 for cousins. We can see the risk follows the genetic relatedness. We repeated that again in yet other, so this first was Swedish data, and then we did it again, Denmark, Finland, Israel, and Sweden. And we can see that there are some differences, but essentially they remain. So we can also quantify the individual risk. And then it's of course, it's a question how family members or clinicians, how can we use these measures? So in research, we are using relative risk, and that tells us something about etiology. But maybe for an individual, you want to know the prevalence, what is the percentage, the probability for me. And these are two different concepts which are tricky. So we saw in the earlier slide I showed you from Australia, where the prevalence was quite low, but still the increase in relative risk was the same as Sweden and Denmark. So the relative risk usually works quite fine in finding the kind of the causal and risks, but for a prediction it may be different. But we can use the relative risk, look for my prevalence, my probability as a basis, and then start multiplying maybe. And then is a question, of course, how do we interpret these things, because it's very difficult. When I cross the street, probably my relative risk of dying increases with at least 80 compared with if I stayed. But I do it every day, I can look around, so I take the risk anyway. And I think enumerating these risks for autism and other disorders as well maybe can help us to relate and reduce part of the stress if we just know the kind of basic numbers. And this is an area we're working a lot in cancer epidemiology. So when you have cancer, the first question is, how long will I live? Will it come back? All right, so this, the summary will almost end my talk, I think. We conclude that the heritability is high, is kind of 80. And there are only few genes that have been isolated. And this also shows that there is a lot left for the environment. And the environmental factor may also act through gene-environmental interaction, which is even harder to measure, so we haven't come anywhere there almost. There are regional differences which are worth exploring. And then I wanted to go through some case studies. I'm not sure if I should just stop here, or if I should dive down in. I can. So this is one example in how we're using the registers. Is it time for this one? 2 minutes. Okay. So again, we're using the Nordic registers. The exposure we want to examine here was gestational age, and that has, in terms of preterm births, this is a well-known risk factor, has done many times before. So what was lacking here, I felt, was the details. So using the whole Swedish population, we could look at gestational age by week instead. And we can do the same in Finland and in Norway, and we can combine it. And there is not so much confounding adjusted for, but we can adjust at least for birth year and maternal age. And we see, we produce these figures. It was published 2020 in PLOS Medicine, and we can see that the risk for autism is lowest at week 40, and then for each week before and each week after, it increases, and it's quite clear. So it's one example how we can use the registers. Shall I stop or do another one? Okay. So I'll skip the IVF thing. I'm happy to discuss it if anyone are interested afterwards. So this is another example of parental age. So parental age have been examined a lot. It's a well-known risk factor. So there are studies on maternal age first, because those are mostly measured. And then later study, the first one led by Avi Reichenberg from Israel in 2006 showed also there is an effect from paternal age. And what about the joint effects? So we did that again in the same collaboration as where we did the heritability. So this is data from Sweden, Denmark, Norway. Norway used a service register, so that was a different ascertainment. Israel contributed with a case control study. We used information about the Israeli population size to reweight that information so we could make it applicable for whole Israel. So again, using statistical methods. And then we put it together. We are estimating the risk of autism with a reference group, which I actually cannot remember here, but it should probably be 25-year-old mothers and 25-year-old fathers. And then look at it jointly. And we see the risk profile here. So we have maternal age on that axis and paternal, and it starts young and goes older in both directions. And what we would see if there were one independent effect of the mother and one independent effect from the father would be a flat plane, and it would be tilted in the direction of older father and older mothers, but it would be flat. But when we start the kind of shapes, it shows there are some kind of interactions. And what we see here is then we have a kind of a safe area, which is green, a small pond, and then the risk grows in all directions from this area. So it's not only older father and older mothers. So it could be interpreted that if I have if I have kids with a mother who is 40 years old with a certain risk, it may not be safer for me to have another kid with an 18-year-old mother, because maybe that would increase it even further. So, and just to show that these are the relative risks, I also created this figure which shows the age of parenting on the Swedish population, but representative of this. So we can see, of course, that essentially all kids are born in certain age groups. Shifted slightly, so the father tends to be 4 or 5 years older than the mother, but then it's almost empty land out here. So, and then one can argue, what is this? I think one message is to look at it in more detail. So it's a continuum. It's not a category. You're not old or young. It's a kind of continuum. And then jointly. And what could this mean? So we speculate that maybe there is some genetic confounding going on. And maybe that tells us something if there are couples where the mother is 49 and have a kid with a 15-year-old man and reversed and things. So maybe there is a kind of a selection there, who knows. We did not adjust for social factors, partly because we didn't have them, but we were not sure either that that would be appropriate, but that would be a different story. So, okay. Thank you.